Nicholas is with us. Tyler is with us. Now let's see who else we got here. This is thermo, though. I need to write that up here. I think what we're going to study today is transient. But we'll see. All right. Welcome, everyone. Let's see who we got here. We have a good crowd. We got William, Alex, Braxton, Bryce, Nicholas, Reagan, Taylor, Tyler, Brian. I wonder if I left anybody out. And let's see. Nathan, Mohammed, Daniel. Hopefully I didn't leave anybody out. And welcome to Thermodynamics. See, I'm getting a late start today. Did you have any questions for me?
Yes, Mr. Griffin, can you go over the 4-62 problem?
I would love to. What is 4-62 about, Mohammed?
It's about the heat exchangers.
Oh, yeah. Let me find it. 4-62. Okay. Now, you've got air coming in and going out, and you've got water coming in and going out. You're going to need two different PV diagrams, Mohammed. You're going to need one for air. For 462. Mohammed, was this part of your homework?
Yes, sir.
Good. I don't mind going over homework. You're going to need two diagrams. You're going to need one for air, and you're going to need one for water. Now, the one for air, you don't have a vapor dome.
Yes.
It has isotherms on it. Now, let me read it here and see. You got air coming in at 500 K and it leaves at 330 K. So you got 500 and 330 K. And we've learned that heat exchangers are isobaric. So this is occurring at 200 kilopascal. it leaves at 330. It enters at 500 and it leaves at 330. So it enters at 500. This is state one. And it leaves at 330. Mohammed, did you have that process for the air on your PV diagram?
Well, actually, no, because I was confused on that PV diagram. So it's
That's
like, I was
okay.
like, well, how to do that?
That's okay, but now you know. See, you need
Yeah.
two different diagrams. Now on the water, let's see if we can do the water here, Mohammed. Now, if I do these diagrams, will that be enough? I bet you can do the rest. What do you think?
Yes, just the PV diagrams.
Okay, well, let's do that. Now let's look at the water here. Shown in is used water at 150 to 80. Okay. The water comes in. Now this is liquid water. It's liquid water. At 15 degrees Celsius, 150 kilopascals. Well, let me draw the 15. Let me draw the 150 kilopascals. That's what I'll do. That's way down low, you know, at 150 kilopascals. I mean, way up here, it's something like 22. It's 22 megapascals, isn't it? And this is only 150 kilopascals. That's way down low. So we'll go back here to your tables and find water and start snooping around. And 150 kilopascals. Has a temperature of 111. There's an isotherm that comes through here of 111 degrees Celsius. But see, that's not what we have. We have 15 degrees and 80 degrees. Well, there's an 80 degrees in here. I'll draw it for you. Here's your 80 degrees. Oh, gee, kind of got messy there, sorry. That's 150, 111. There's your 80. And there's also a 15, and I'll fake it. It's way down low. Now we're going from, read it, let's see, I got lost. We're going from 15 to 80. All right. This was 15 here. This middle one is 80. And that one's 15. I tell you what we're doing. We're going from here to here. It's a little bitty process. You don't need to use black for that. There it is. There's your process. There's there's 3 to 4. State 3, state 4. Tell you what, let's do We're going to zoom in. We're going to get one of those zoom in cameras. And we're going to zoom in. And this one's the 15 degrees Celsius. This one's the 80 degrees Celsius. And this right here is the 150 kilopascal isobar. There it is right there. 150 kilopascal. We zoomed in. We took our camera and we took a picture in here and we zoomed in. And here's state 3 and here's state 4. And we're going from 15 to 80 degrees Celsius at 150 kilopascals. Isn't that what it says? Yeah, that's what it says. And now Mohammed knows what it looks like. Are you satisfied now, Mohammed? Are you happy? Earth calling Mohammed.
Yes, I'm happy.
Okay. Do we have any other comments or questions from anybody?
Yeah, on that last PV diagram, is either, or I guess, would state 4 be on the vapor dome?
No, it does not enter the vapor dome. It's
Not, I'm sorry, just like on the very edge of it,
No,
the
it's not even
saturated
on the-
liquid.
No, it's compressed liquid.
And how do we know that
Not.
both states are compressed liquid?
Yes. I'm sorry. Are you asking me how do we know that?
Yes, sir.
Because you don't enter the vapor dome till you get to 111. Tell me your name, please.
This is Taylor.
Taylor. Now there is 111, Taylor. There's 111 degrees, and it's right there on the vapor dome. That 111. That 111 is on the vapor dome. There's your vapor dome. The 111 intersects the vapor dome, but the 50 and the 80, they do not enter the vapor dome. Taylor, did that answer your question on that?
Not, I'm still confused. So the 111 is what we found in the tables at 150 pascals or kilopascals,
Right. And that'll put you right on smack dab on the vapor dome at the 150 kilopascals and 111 degrees Celsius. That is what they call saturated liquid. But see, out in here, we're compressed liquid.
Okay, I think that's what I needed. Thank you.
Okay, good, excellent. Anybody else? Okay, well, let me see about your homework and all that. Let me look and see here. Today's Tuesday, the 13th. I think your exam is available today. There's a little room down here. Your exam is available now. It's a take-home exam, and it's due Friday. It's available now. And it's due Friday. I don't think there is any homework assigned for today. Now, you had some homework last Wednesday that you can turn in, and I'll put some grades in the grade book, but you're going to be busy doing that test for today, so that's where we are in our schedule.
Professor, so it is definitely due on Friday. I thought it was due on Sunday. I just want to make sure I'm not mistaken.
If you check the, who am I talking to?
This is Nathan.
Nathan, thanks for asking, Nathan. If you check the Blackboard, I think it says 16th. And I think the 16th is Friday
Friday. Okay. Okay.
at midnight. So you could start working on it, probably along about 10 o'clock Friday.
Sounds good. I'll do that. Maybe 11. I'll start at 11.
Maybe 11. All right, now the topic for right now, I wanted to do a couple of things. I wanted to do a nozzle with English values. That'd be good for us. And then I wanted to do a transient process. But I'm gonna erase all this if I can. If you're happy, if you guys are happy, I'm gonna erase. But before we do this transient process, this is a review thing about nozzles. I think there's a nozzle on the test. I forget. But it's in Inglés, señor. Only that the way they spell Inglés. I think that's how you say Inglés, señor. And this problem is 4104E. We have got to know how to work in English. Metric is wonderful, but there's still a lot of English stuff out there. When you go and buy gas, you don't buy liters, you buy gallons. When you stand on the scales at the gym, it doesn't say newtons. It doesn't say newtons. It says pounds, doesn't it? English, we got to learn how to work in English. Okay, now this is 4104E. Now help me find it. Okay, I found it. It's a nozzle. So you know what you're supposed to do. You're supposed to draw a device sketch. This is air. You've got 1800 Rankine coming in. 30 PSI. Now they put a little A on there. PSI absolute. Just to confuse us, I guess. And 90 feet per second. Coming in. And then it exits at 1500 Rankine. They always cool off. 13 PSI. The pressure goes down. They cool off, but it speeds up. And they want to know the exit velocity. They want to know what the exit velocity is. Well, we could draw a PV diagram. That'd be good for us. I think I'll shut up for about a minute I'm going to let you draw the PV diagram. And then I will, and we'll compare notes. How's that? Go for it. Okay, well, let's draw that PV diagram. Now we've got a 1800 Rankine, and you know isotherms kind of go like that. And you got 1500 Rankine, and they kind of go like that. Now the pressure goes from 30 to 13. So let's say 30 is here, okay? We're located right here, call that state 1. And then it goes to 13. We could say 13 is down here at state 2. And here's your process. There you go. You draw your process, put an arrowhead on it, and you've got your process from 1 to 2. There's your PV diagram. All right, we've done our device sketch. We've labeled it. We've done our PV diagram. Now let's write our first law of thermodynamics. Well, for a nozzle, it goes like this. Now, do they give us the velocities? Isn't that? Oh no, they give us this one. Look here, they gave us this one, but we don't know that one. We're going to find it. Tell you what, let's do a little algebra. See if you can get to here with me. Can you get to there? Did I do that right? No, I didn't. I got it wrong, didn't I? And how about now? I think I got it right now. Okay. Now there's a couple of ways to go about this. One way is you can just look those up. If you're lazy, let's do that way. We'll do it that way. Go to the back in the English section under air and look up 1500 Rankine. And it says, uh-oh, they don't have a 1500. You got to interpolate between 1480 and 1520. Well, that's not hard to do. So I'm gonna get that. Here we go. I'll write it out if anybody needs me to. Well, I'm getting this H2 at 1500 to be 369.3. That's good enough. BTUs per pound mass minus H1. Now H1's at 1800. Let me find that. There it is. Now that one's given. That's 449. 449.794. Now, did anybody have trouble getting that H2? If you did, just speak up and we'll write it out if you want. Well, nobody spoke up. And now this is given. That's 30 feet per second squared over 2. Oh, gee, I'm running out of room. Minus V2 squared over 2. Well, there's your equation. But we've got to fix the units. Units are terribly important. We got it made here. There's only one unknown, but see, the units aren't right. This is going to be feet squared per second squared over here. And this is BTUs per pound mass. Let me show you how you can get from one to the other. I just need a little room here someplace. How about up here? Now what I've got there is feet squared per second squared. What I got there is BTUs per pound mass. Now a BTU is equal to 778.15 foot-pound period. And we were dividing by pound mass. I've got to convert these units somehow. So far, so good. Now, a pound force is equal to 32.2 feet per second. Pound mass, feet per second squared. That's what a pound force is equal to. If you don't understand that, just speak up and I'll show you. Now here's where we're at so far. We got rid of our pound forces. See, the pound forces cancel. And hey, look at here, the pound masses cancel. And look, we have feet squared per second squared. So what we've got to do is on this left-hand side, we have to multiply everything here by 5 and multiply it by 32.2. I've shown you the units up here. And if you do that, what you'll have is feet squared per second squared, which is what you have on the right. Now we've got an equation. Look, a great big old equation here with only one unknown, and we can solve for the exiting, or state 2, you can call it, exiting velocity. I'm going to shut up, and I want you to solve. Plug all this stuff in for me, please, and find the exiting velocity . Well, I got an answer. Anybody out there have an answer yet? Let me go to one of my excellent students here. How about my William? William, unmute and say hello, please.
Hello?
Hey, William, have you plugged in all this and gotten this exiting velocity yet?
I have not.
Take your time. Get your calculator out and plug all that stuff in. How about Alex? Alex, unmute and say hello, Alex.
Hello?
Hello. Hey, Alex, have you plugged all this in and gotten that exit velocity yet?
I've gotten a number. I don't know if
What'd
it's
you
the right
get?
one. I got 4,535 feet per second.
Well, that's not what I got.
Okay, I'll try it again.
Your square root.
You gotta take a square root.
I thought I did.
I got 2010.5.
I got that too.
I got 2008.
I got 2008.
I got 2013.
I got
Guys,
2010.5.
how can we get different numbers? There's only going to be one number. Here, I'm going to do mine again. I got 2008, but I'm going to do mine again. You can't get different numbers. No, I get 2008 again. Are you guys, let's put it this way. If you got 2008 feet per second, say uh-huh.
I did it again, and that's what I got.
Yay! I need another uh-huh.
Uh-huh.
There's one. Yeah, I need another uh-huh. I'm not getting another uh-huh. I guess that's all the uh-huhs I'm going to get. Huh? Hey, there's one. Now let me show you another way of doing it. Actually, that's probably the best way to do it. But there is another way, and let me show you that. This here, you know what that's equal to? There's some room right here. I can squeeze it in right in here. Yeah, there's some room right there. You know what this is equal to? That's equal to delta H, isn't it? Final minus initial, that's delta H. And we have an equation that goes like this. C sub P delta T. Now, C sub P for air, I happen to have memorized. It's 1004. Is that right? BTUs per pound mass, Rankine. Oops, I didn't leave room for my delta T, did I? Let me scoot that over there. We better look that up. Look in the back and snoop around and see if you can find for air. No, that's metric, isn't it? That's no good. Guys, that's metric. It's 0.240. You know what I was thinking? I was thinking 1004 kilojoules per kilogram Kelvin. And we're not in metric, we're in English, senor. But now we know what the change in temperature is. It's, well, it's minus 300 Rankine, isn't it? Okay, now we're going to do that this way this time. But still, don't you have to multiply by 778 and 32? See this stuff here, instead of using the integral tables, we're going to use 0.240 times negative 300. I think you'll discover it should come out pretty dang close. Then we're going to multiply by this. We're going to solve it. We're going to get our answer. This time I'm going to shut up, and I want you to solve it. But don't use these. We're using a different model. See, we're using a different model that's it's not as good. This model here is superior. But go ahead, solve it, and let's see what happens. Here goes. Well, I got a little different answer this time. I'm not sure this is right. I'd want to do it again a couple of times. I'm just going to round it off to 1900. It's really 1899.7 something. Anybody getting 1900 for the exiting velocity?
Uh-huh.
That's what I got.
I heard an uh-huh. I must have done it right. Now I'm going to put a happy face on this one because it's a better model. This one here, this model is not as good. And I'll tell you why. Because we're dealing with temperatures that are pretty dang hot, aren't they? 1800 Rankine? Gosh, that's really hot. See that value there is the value for air at room temperature. And C sub P is different at 1800 Rankine. But it turns out it's not terribly off. What are we off by? Well, quite a bit. 108 maybe. This is a better answer. Is that what I got when I did it before? Let me look and see here. Yeah, that's about right. Mm-hmm. Okay, well, that was fun. Yeah, you're off by about a little over 100 feet per second when you use the inferior model. Any questions on that?
Professor, this is Tyler. I do have a question on the equation we wrote out. On for V1, we have 30 feet per second. Isn't V1 90 feet per second?
Oh, Oh, it is.
Because that's
It is.
instead
I
of
screwed
2008, I got 2010.
In fact, that's the correct answer. I wonder why these are a little different. Was that Tyler?
Yes.
Honkin' thank you point for Tyler. Now here's where I screwed up. Let's see if I can find it here. Ah, here we go. V1 is 90 feet per second, guys. This was a screw up. That's supposed to be 90 feet per second. Tyler, I appreciate you so much. Now, if you do that, I did this before and I wondered, well, why are my answers slightly different? What you wind up with is 2010. Is that what you got, Tyler?
Is that what I got too?
Yeah, that's what I got.
Proud of you guys. Proud of you guys. But now if you do it this way, well, you'll get a different answer here too, but not much different.
For that one, I actually got 1901 with the
That's what I got too. I got 1901. I did this before. Now, why that's so similar, I don't know, because there's quite a difference. Well, there's really not that much difference. 2008, 2010. That's why I got fooled on that. But I put in the wrong velocity there, and thanks to my excellent students that are awake, I appreciate you being awake. But now we know there's more than one way to do this stuff. Okay, we're going to talk about, if there's anybody else, that was wonderful, you guys. If there's anybody else, well, we're going to erase this and do a transient problem now. Okay, well, here goes, we'll erase this. But see, units are important. It's also important not to screw up. Try to remember that. But units are important too. And you have to, you got to make sure you got the same units on both sides of an equation, or else it's no good. Okay, we're going to do a transient problem now. And this one here is problem 483. We're going to do 483. Now let me find it. Okay, 483. This is a transient process. It's a 2.5 liter tank. Okay, well, here's your device sketch. $2.5 liter. We really need that in cubic meters. See, there's 1,000 liters in a cubic meter. So if you move that decimal over, you'll have 0.0025 cubic meters. And there's a line here. I don't know what's coming in, the air maybe? No, it's ammonia. We've got ammonia coming in. There's a valve here. And we're going to open that valve. But initially it's empty. It's empty. And then we open that valve and ammonia comes in from a line with saturated vapor at 25 Celsius. Okay, well, here's state one. And now we'll draw state two. Now we've got ammonia inside. Do we know how much? They don't tell us that, but they do tell us the temperature is 30 degrees Celsius. But now this stuff's coming in at 25 degrees Celsius and it's saturated vapor, they said. Saturated vapor. Okay, 25 degrees. All right. Oh, they told us there's 10 grams. We now have 10 grams of ammonia in our tank. We open that valve and there you go, the ammonia comes in and it's 30 degrees. It came in at 25, but it's going to be 30 degrees. Whenever you fill these things with a gas, they heat up. They heat up, they get hot. We're doing problem 483. It's called a transient problem. It's a transient process. It's not steady state. See, steady state, nothing changes with time, but stuff is changing with time. I mean, it was empty, and now it's going to have 10 grams in there. The pressure in here was 0, and now the pressure is going to be, well, I don't know what it's going to be. Do we know the pressure? Let's read it. Well, we don't know. They want us to find the final pressure. Okay, we'll find it. That'll be good. But we need to draw our PV diagram. So let me draw that. Okay, we got ammonia now. And we know it's gonna do something like that. But see, state 1 is way the heck out here someplace. Because the pressure is 0. If your pressure is 0, you're on this 0 pressure line, right? It's empty. It doesn't have any pressure. And then it, according to, if you read it, it says they keep the tank and its contents at 30 degrees Celsius. Well, there's a 30 degree isotherm with ammonia. Why don't we go to ammonia just a minute? Go to the back and help me find ammonia. There it is. I always go to the vapor dome chart first. You know what? 30 is kind of in the middle. I'm on table B.2.1. Table B.2.1. 30 degrees is kind of in the middle, so somewhere way out here is state 1. And 30 degrees is coming up here like so. Until what happens? Well, let me read it. Well, we don't know what the final pressure is. I tell you what we do know. The ammonia coming in is saturated vapor at 25. See, this 30, here, let me keep on going. This 30 will come up here someplace, hit this, go over here flat, and go up. There's your 30 degree Celsius isotherm. But see, what we're at is at 25, and it's right about here. I could draw that for you. Here's your 25 degrees Celsius. But we still don't know where state 2 is. This is your incoming state. I'll put a little I for that, okay? That's your incoming state. It's at saturated vapor at 25 degrees. And you're right there. But state 2, I don't know where it is exactly. Let me keep reading here. We're doing problem 483. We're going to cool the tank, fill it slowly, keeping the tank and its contents at 30. Find the final pressure, and then we'll close the valve. Well, I don't know where state 2 is. It could. What is this pressure here at 25 degrees? It's 1,003.2. That's what it is at 25 degrees. Coming in. I don't think the pressure is going to be bigger than that. It's probably going to be that or smaller. Probably smaller. State 2 is probably in here somewhere. I'm just taking a guess. I don't know for sure. But I tell you what, we know we're coming in here from state 1. Here's our process. It might go up higher than this, but I don't think it can go higher than 103. If you get 103.2 kilopascals coming in, I don't think you're going to get a pressure higher than that. If you could leave that valve open all day long, and it would fill to 1,003.2 eventually, but it's not going to go higher, probably lower. Probably state 2 is right there. Put an arrowhead on it. Ta-da, there you go. Okay, now what? Well, we've tried to do our device sketch. We've tried to do our PV diagram. We've tried to label everything. What's next? Well, you have to use the first law of thermodynamics. But see, the first law for transients is that big old long thing. I'll show you how it goes. It goes M2, U2 plus, there's some terms in here that we don't need. Velocity, kinetic energy and potential energy terms, we don't need them. Minus M1, U1, and again, we can just neglect the kinetic and potential terms. And then we have a Q minus W plus an incoming mass. Again, you have some kinetic and potential terms that you can neglect. It's a big old long thing. It's the first law of thermodynamics for transient processes. A little bit ugly. Now let's see if we know anything. This term here you can get rid of. It's 0. Now how come that's 0? Let me ask somebody. Let's see. Let me ask my friend Braxton. Braxton, unmute and say hello, please, Braxton.
Hello.
Braxton, how come I can cross that term out for the mass at state 1?
Because it's empty. There's no mass in there.
Because it's empty. Good going, Braxton. We can get rid of that. Now here's something else we can get rid of. Do you see this exiting term here? It's 0. Let's go to my friend Brian. Brian, unmute and say hello, please. Earth calling Brian. Earth calling Brian. Come in, Brian.
Hi, I'm Brian.
Yeah, there you are. Hey, Brian, how come I could cross out that exiting term there, Brian?
Let me look at it. I'm sorry, I was distracted. I have a baby.
Hey, Brian's got a kid there that's crying. You better take care of your kid.
Okay.
Let me go to somebody else here because I couldn't hear you very good, Brian. You need to turn your volume up. Daniel, unmute and say hi.
Hello.
Hello, Daniel. How come it's okay for me to say that's zero, that exiting term there? How come?
Because it's not exiting, it's entering.
That's right. There's nothing exiting. There's ammonia coming in, but there's nothing going out. Now, as long as I got Brian on the line here, Brian, this Q is zero too. How come? How come that's zero? Now, wait a minute. I lied to you. That is not zero. In fact, I think they tell you what it is, don't they? Let's see. Oh,
They
we're
ask us
supposed
to
to
find
find
it.
it. Oh, we don't know what it is. We're going to find it. We'll get to it. But now back to my friend Brian. I think I'm talking to Brian. Brian, I can get rid of this work term. How come that work term is zero, Brian?
I would say because there's no piston doing work or anything like that in this situation.
It doesn't do any work. Piston, there's no piston going up, lifting anything. There's no turbine blades that are spinning, running a generator. There's no work. All you got is somebody opens the valve and some ammonia comes into this tank. There's no work. Now, the thing is, we know what this incoming mass is. They said it's 10 grams. So I'm going to circle it. And you know what? We could look this up. Go with me to the ammonia. I lost my page there. And help me find ammonia vapor dome. And what we want is 25 Celsius. There it is. Ammonia, 25 Celsius, saturated vapor, incoming enthalpy. Here, let me write it. The incoming specific enthalpy is, I got 1463.5. Can you find that? Kilojoules per kilogram. Can you find that in table B.2.1? Did I get that right? I think that's right. So see, we know what this is. Look here. We know what it is. We know what the incoming mass is. It's, well, you got to put it in kilograms. It's 0.010 kilograms. So we know that. Hey, the mass is at state 2. It's whatever came in is what you're left with. It's 0.010 kilograms. So what we have here is a, oh, no, wait a minute, Auga, what about U2? What do we know about U2? Ah, it's at 30 degrees, but do we know anything else?
Professor, what?
Say again, please.
I'm sorry to interrupt. This is Nathan. I understand that ME is 0.01 kilograms, but I thought MI was 0. Or
No, M2 is 0.01 because whatever comes in, the incoming mass, okay, I got lost. They said that 10 grams comes in. That's M2. And that's also the incoming mass because that's what came in.
I understand now. Thank you.
Yeah, thanks for asking. Okay, now here's what we got to do. We got to find the specific volume. At state 2, I know the temperature. The temperature is 30 degrees Celsius. They said so. It's an isotherm. But I can get the specific volume at state 2 because it's equal to the mass, which is, well, we know what it is, divided, no. It's equal to the volume divided by the mass. Well, the volume at state 2, it hadn't changed any. It's 0.0025 cubic meters. And the mass at state 2 is that the 0.01? Yeah, that's the 0.01 kilograms. Hey, we can get the specific volume at state 2. Go for it. Get your calculators out. I could almost do that in my head. I don't need no stinking calculator. Little v2 is going to be 0.25 cubic meters per kilogram. Did I do that right?
Uh-huh.
I don't trust myself. Would you say it's okay? Yeah, okay. Now look here. We have ammonia. We know it's ammonia. We have the final temperature, and we have the specific volume, and now we're going to get the pressure. Here we go. I need some room here someplace. There's some room right in here. Look here. We'll just carve us out some room here. We know we're in the superheated vapor region. This is superheated vapor. So go with me to ammonia superheated vapor. Now this is at 1,000. I think it's going to be less than 1,000. So we're going to have to shop around. What we want is 0.25 at 30 degrees Celsius. Well, you have to shop around. This might take you for a while. But I'll tell you where it is. At 30 degrees Celsius, we are between 500 kilopascals, which has a V of 0.28103. And 600 kilopascals, which has a V of 0.23152. See if you can find those in table B.2.2. And see, what we want is this pressure at state 2 when this is 0.25. Well, see, 0.25 is between these. Can you find these numbers in the superheated vapor ammonia table at 30 degrees? The 0.25 is between those two numbers. I'm going to wait till I hear an uh-huh. See if you can find those numbers. Find the 23152, the 28103, and tell me uh-huh. Yeah, there's somebody. But see, what we really need is this U2. We need the U. In this equation, we got everything else. Look, we got everything else, but we don't have that U2. If we can get that little U2, we can get the heat transfer. Oh, by the way, we can also get the pressure. Let's get the pressure first. Okay, we're going to interpolate now. We're going to interpolate between these two and get the pressure. I'm going to shut up. We got time. It's good for you. You know, Now let's see which one are we closer to. 23 to 25, that's 2. 25 to 28, that's 3. I think you're probably closer to the 600. You're probably something like 560, something like that. Go for it. Find P2. I'm going to do it also. You do it, I'm going to do it. Go. Okay, guys, I got P2. I think it's 562.7. And I'll wait till I hear a couple of uh-huhs.
Uh-huh.
Hey, boss. So,
Uh.
hey, I heard one. I'm waiting for another uh-huh.
Uh-huh.
Hey, yay, good going. And now we're going to get this specific internal energy. I need to write these down though. Hang on. Let me find those. At 30 degrees Celsius and 500, that is 1373. And at 600, it is 1368.2. Now we're gonna get the specific internal energy. We're gonna have to interpolate. Go for it. See if you can find the specific internal energy. Well, guys, I'm getting 1370. I'm getting 1370 for the specific internal energy, and I'm going to wait till I hear a couple of uh-huhs.
Uh-huh.
Uh-huh.
Yay, yay. Okay, now looky here. This is our first law of thermodynamics that we just figured out, U2. We got everything we need now. I just need to write in the numbers. And we're going to solve for, oh, by the way, here's our pressure at 2. See it? It's 562.7. Remember, I told you it's going to be less than 1,003. And now we know what the final pressure is. It was 0 to start with, and now it's 562.7. But now we're going to get the heat transfer. Now, they said the heat transfer is negative. They're saying that the heat transfer is negative. Let's see what it is. I wish I had room to write all that out. We can write it out up here. There's room. Here, let me write it out up here. Here we go. Okay, M2 is 0.010 kilogram. U2, we just figured out, it's right, yeah, 1370. kilojoules per kilogram. And we're done with the left-hand side, equals the heat transfer plus, well, the mass coming in is the same. It's 0.010 kilogram. And the incoming specific enthalpy, we wrote that down someplace. Oh, there it is. It's 1463.5 kilojoules per kilogram. So here's our equation, and we can solve for the heat transfer. Go for it. I'm doing it. Well, boy, Joe, you know what? We're getting a negative, just like they said. It's just kilojoules, because see, the kilograms cancel. It's negative 0.935 kilojoules of heat transfer out for our process. Well, we did a transient problem. And are you the class that's going to be doing an exam for me? I think so. It's due. When is it due? Did we say?
Right.
Friday. Friday at midnight. Yeah. Okay. Well, concentrate on that. But here's what we're going to do when we come together again on. We'll be together again Thursday, right? Yeah. I'm going to move on. We're going to talk about stuff, unless you have a question for me. We're going to move on to chapter 6. That's what I plan on doing. Chapter 6. Thursday. So we'll meet on Thursday. And chapter 6, the title is Entropy. That's the name of it. And we're going to learn, that's not on your test. And if I can throw in some review, that'll be good Thursday. But we're going to move on Thursday, and we'll meet, and we're going to talk about chapter 6. So you might want to start reading about chapter 6. But I know you're mainly concerned with doing good on your test. So if you do good on your test, Thursday we'll meet and talk about the wonderful concept of entropy. Any last comments or questions from anyone? Okay, well, let's say bye-bye for now, and I'll see you Thursday at 11. See you at 11 o'clock Thursday. Bye-bye, students.
Bye, Mr. Griffin.